In this video, we're going to extend what we saw in first and second derivative analysis, not to just one function, but to a series of related functions, which we're going to call a family of functions. Those are typically functions that have a common mathematical form, but they have some constants, or what we'd call parameters here, because the constants can change. The key thing is they're not the variable x or t that we typically use as the independent variable. This will make more sense through an example. Here we have a variation on a function we saw earlier in the class, where we include a value a and a value b here, and we want to know what these functions look like. Notice if we change the value of a, we'll get a new graph, which will be related to similar graphs with different a values, and that's what we mean by a family. There's a family resemblance. There's some things they share in common, while each being individually unique. If we let b equal 1, then we can focus in on a particular subfamily, a branch of the family if you like. And this family is the family of a graph we saw before with a multiplier out front. And we know what this does. This does scaling vertically, scaling and flipping vertically. If we can remember the graph that we saw earlier, then we know what the influence of a will be. For example, here's our graph with a equals 1. Let's sketch this out a little bit here. There we go. That would be the graph with a equals 1. If we change a to 2, what that's going to do is scale this graph by a factor of 2, so all the vertical components are going to get twice as large. We can build some anchor points with that. Another way to say twice as large, an important geometric way, is twice as far away from the y equals 0 line. Notice the point at y equals 0 does not move when we scale things. So this would be the graph corresponding to another member of the family, but the family member with a equals 2. We could go to 3, 4, and 5, or 1.7, whatever we like. More interesting would be if we picked a negative value. So what if we had -1 in our family member? That would start to look like that. What that would do would be flipping or changing the sign of all the y components. Where the function was originally positive in y, now it's going to have a negative symmetric y, and likewise on the left-hand side. And of course, we don't have to use integers. We can also use a equals 1/2. That would scale things down towards the axis. It would flatten things out. And we could get a graph like the black line sketched out there. And again, with that sketch, you get some sense of the idea of what we mean by a family. All these functions have a lot in common, but each has a particular characteristic that makes it different from the other members of the family. Let's take a look at the other branch of the family. What we're going to do is pin a down to 1 and change this value, this what was +1 in the denominator now. Imagine we have +3, +4, +5, or -1, -2, -3, variations in that value. Well, what effect is that going to have? One of the ways we can find out is by looking at how the first derivative changed. We didn't need to do that in our earlier example with a, because a was just a multiplier and we already knew what multipliers do. It's less clear what changing this constant in this more complex function here does when it's buried inside the denominator. So let's take a look at the derivative though, with this being our function, so a is hardwired to 1 for now. And what we're going to have is 1 times the bottom minus the top unchanged times the derivative of the bottom, all over the bottom squared. Now we'd like to simplify that a bit. We have x squared minus 2x squared. That's going to give us -x squared. We also have a b on here. And we've seen something similar to this before. What we're going to do is factor that out. We can call that root b minus x and root b plus x, because this we can treat as a difference of squares all over the denominator again. Now we've done some sign charts with this kind of formula already. We know that the denominator is always positive, so if we're going to do a sign chart for this scenario, we would be concerned mostly with the top, actually only with the top, the square root of b minus x and the square root of b plus x. Careful that the square root ends at the b. If we take a look at that, we'll put 0 as an anchor point. If x gets too big, in fact, if it gets past root b, then this is going to go negative. If x is small, we're going to have positive values. If we do the same thing for this term, or this factor, negative root b is going to be the transition point. If x is negative b, then we get 0. But if x is bigger than that, we're going to get positive. And if x is a negative number, we're going to end up with negative values there if it's past root b. And so what does that give us overall? It gives us a nice sign chart that says minus root b and positive root b are transition points. Our first derivative is going to be positive times negative is negative here. We're going to hit root b, negative root b rather. And on this interval, we'll have two positives, so it'll be positive. And then afterwards, we'll have negative values. Notice this only applies for b positive. If we have negative b's, we can't do this funky separation of the perfect squares here, the difference of squares. So this will apply for b being 0.2, 0.8, 1, 2, 3, and so on, positive values only. What can we also do? Well, we found out that negative root b and positive root b are going to be transition points. In fact, they're critical points because we said the slope is negative going up to here. The slope would be 0 at this point, and then before it goes positive, and then it's positive, positive, positive. Before it goes negative, it's going to be 0 again. The slope will be 0, so we will have critical points. And so what we can do is find out what the height of those critical points are. Again, we're using a equals 1, so we'll just have root b on top over root b squared plus b, and that is much better known as root b over root b squared, which is b itself. That's over 2b. That's a perfectly valid way to write it. Some people might like writing it as 1/2 1 over root b. Doesn't matter to us. The other critical point is going to be with negative root b all over negative root b, that's our x value squared, plus b, that's in the formula. And we're going to get the same thing essentially because the square here, when we square the negative value, it becomes positive. The only difference is in the numerator, we do not get rid of the negative sign. So we're going to have a negative y coordinate. So what we're tracking out here is if we have a critical point at root b, where is it? Well, it's going to be up top, it's going to be positive, it's going to be at this y coordinate. And if we look at the negative root b critical point, it's going to be below the axis, it's going to be down here somewhere. So this required a little more in-depth analysis, but we can follow up and use that to sketch some different members of the family. Let's do the easy one, b equals 1. If we do that, we have the critical points at square root of 1, comma, the 1/2, 1 over root 1, which is much better known as 1/2. So let's actually write that. So 1 and 1/2. And the other one was symmetric to that. It'd be negative root 1, and it's exactly the same thing here, so negative 1/2. So if we sketch that out on our diagram, draw our axes, our function versus x. Let's make this one here, give us some scale, and yeah, we'll keep it symmetric, negative 1 and 1. So at this value for b, we have a critical point at 1 and 1/2, so here. We knew the function went through 0, 0, and we also know the rest of the shape, which is the concavity from before. Don't expect that to have changed. That's essentially the graph we had before, except with more detail. We now actually have the y-coordinates on the critical points. Where it gets more interesting is if we can adapt this a bit. And because we have square roots, let's pick a nice value like b equals 4. That works well with critical points that have square roots in them. So the critical points here are going to be at the square root of 4 and 1/2, 1 over the square root of 4. And that's better known as 2, and 1/2, and another half is 1/4. Interesting. And we saw the same relationship going back a page if you need to. The other critical point was at the same x but negative and the same y but negative. So we're going to have those points. And what does that do? Well, it means that for this graph, we're going to go out to 2. The height that we're interested in is going to be a quarter. Let's sketch it out here. And that is going to be the peak. We're going to be increasing until there and then coming down and flattening out from there. And likewise on this side, this is our critical point. We're going to be decreasing until we hit there. Let's draw it a little higher. And then we're going to bend down. So what we see by increasing b is that we're flattening out the curve, we're stretching it horizontally, and we're also compressing it vertically. It's not a simple relationship like a scaling or shifting, but we can see that this function here is still related to the original family member at b equals 1. They just have the important ingredients like the critical points and the transition, the points of inflection at different locations. And you can imagine in different scenarios, trying to model a physical system or a financial system or something in sociology, you might need to tweak a particular member or a particular formula for a function, pick a different member of the family to precisely match what you're seeing in nature. And that's the kind of structure we can work with using families of functions and using the kind of analysis we've seen with the first and second derivative sign charts, which can let us explore these kinds of families much more easily and much more thoroughly than trying to do tables of values or other more mechanical approaches to graphing functions. Quick note about a and b being possibly negative. Certainly we talked about a being negative before. That would involve or create a vertical flip. And so that would change the character of the graph from this kind of shape to a shape where it goes down first and then comes back up. So that would be a negative. If we made b negative, there could be a whole pile of other stuff happening. Why is that an issue? In all of our sign charts earlier, we relied on x squared plus b being positive. And if that's the case, or if we break that rather, if that is possible not to be the case, if we have x squared plus a negative number here, then x squared plus b can be 0, and all of a sudden we're going to introduce vertical asymptotes, certainly discontinuities, and our usual guess for that would be a vertical asymptote. Whole other kind of problem there, so the graph would look nothing like the families we saw before. So it's possible that there's certain branches of the family that look reasonably similar, but you can change the parameters into other ranges where we get very different looking family members. That's just the way this goes usually. In many examples, we will limit our focus to typically positive or negative constants in these families just because they have more in common and because the analysis is similar if we rely on a and b here being positive quantities. Last but not least, let's take a modeling example where we say, I have this family of functions, but I'd like to have the critical point hit at a specific location. At the point 110, I want to have this graph peak there and then come down. Again, we know what the family members look like in general, but how can we nail it down to this specific member that has this specific property? Well, what we can do is say, if that's going to be our critical point, we know that the derivative at 1 is going to equal 0. We also know that f of 1 is going to equal 10. Those are two mathematical statements we can derive from the family having its maximum at the point 110. Once we have those mathematical statements, we can go back to our function and actually see which family member satisfies these. Well, remember when we said that the critical points of this function were at root b and b, root b and negative root b? Well, that makes this easy because we want the critical point to occur at 1, and so the b value we have to make that work is going to be 1. Once we have that piece of information, then we can talk about the value of the function. We also need to know that f of 1 is 10, but f of 1 plugged into this formula here is a times 1 over 1 squared plus, we already have our b value, so that's 1. And so we get a over 2, that has to equal 10, and that means the a value has to equal 20. If that's the case, the family member we're looking for is 20x over x squared plus 1. Matches the desired properties. Desired property here, in fact, maximum at 110. So we can use our analysis from earlier to hone in on a particular member of the family that has a certain behavior that we're looking for. You'll see practice problems that have the same kind of flavor as you go through this unit.